We're now going to talk about atomic and molecular spectra and how these are explained using the concept of quantization. Okay, so let's first talk about the facts about light. Some facts about light. Light you can separate into different colors. So, for example, if you have a flashlight here running through a prism, you're familiar with this. It separates into the colors of the rainbow. And remember, the wave model of the light allows us to explain this. We say each color is associated with a different wavelength. So waves with different wavelengths are bent at different angles. Okay, and of course you have light that you can't see. Invisible light would be in the infrared and radio waves. That's past the red, or beyond the violet end of your spectrum, you have the ultraviolet, X-rays, and gamma rays. Okay. Now, if you were to get light from a source that has a high concentration of atoms, like a filament from an incandescent bulb, okay, and you run it through a prism, you get what's called a continuous spectrum. You get a continuous band of color. So something like this would be an example of a continuous spectrum. Okay. Continuous as opposed to what you might get when the light source has a very low concentration of atoms. Okay, so for example, if you have a hot gas, so you remember in the gas, the atoms are relatively significantly far away from each other on average. The spectrum you get, okay, from a sample that has a low concentration of atoms will look something like this. You're not going to get a continuous band of colors. You're actually going to get mostly dark areas with very bright lines in between. Okay, so what you have here is what you would call the line spectrum, or a discrete spectrum that's observed for this particular sample. Now, each atom and molecule, it turns out, has a unique spectrum. It's sort of like its fingerprint. So, for example, this spectrum right here that I'm showing you, we have red, that looks like green, bluish green, and then you've got violet right here. This characteristic spectrum that you see here is unique for hydrogen. Okay, so if you see this spectrum, you know it comes from a hydrogen atom, or it comes from hydrogen atoms. Okay, so we can use the light that's produced by atoms and molecules as a way of identifying them. And that's how you can tell what's out there in outer space without having gone there. Okay, you base it on the light that you see. So an example, a very nice website that you can go to see all these emission spectra from atoms would be this site right here. What was that site I read, right? Jersey.uoregon.edu. So just do a search for Jersey U Oregon, University of Oregon.edu. Okay, and there's the lab terminated. Let's see. What was it? Elements spectrum. And you should be able to find your first link to be this Java applet right here. Just allow the applet to run. And if you click, you can see, if you click on emission, okay, that's the light that's produced by the atoms. This is characteristic for hydrogen right here. Okay, so this red line occurs at around 656.8 nanometers. That's around 656 nanometers. So this is given in angstrom, so that's 6,564. And angstrom is a tenth of a nanometer. So that's 656 nanometers. This thing right here that's bluish is around 487 nanometers. Okay, so if you drag your mouse, it brings up a cursor that tells you what the wavelength of the lines are. Now, if you're dealing with neon, that's the neon lights that you see in those signs, outdoor signs. Okay, these are the different colors. It's the characteristic pattern of light that's produced by neon. Okay, so this is carbon, sodium. Okay, the brightest of these lines that you typically see is this yellow line right here. Is around 589 nanometers. That's yellow light. Sodium lamps have a characteristic yellow color, and that's due to this wavelength right here. Okay, and so you've done your flame test in your freshman lab, test for different ions. So if you do a flame test for sodium, you get a yellow light. That's the wavelength of that. That's the same yellow color that you see when you spill your soup on your gas stove. Okay, so you have salt, sodium chloride in your salt soup. Okay? Or if you electrocute a pickle, that yellow light you get, that's the same sodium. Okay, so yeah. Do a Google search for a pickle electrocuted, and you'll see that it produces a yellow light. That's due to sodium. All right. So anyway, that's a characteristic spectrum. Okay. So the thing is, why do atoms and molecules have discrete spectrum? Why do you have these lines? Okay. Why can't they just produce all sorts of different wavelengths? So how do you explain that? Okay. Before we actually go to the explanation, let's talk about absorption spectrum. The same thing. Absorption spectrum refers to the light that an atom or a molecule can absorb. So if you have a light source, let's say you have a continuous light source right here. Imagine this light source. You saw this one earlier. Imagine if you did not have this gas, what would you have seen here? A continuous band of colors. But if you pass it through, a gas sample, okay, some of those colors are blocked out, right? So you get these dark lines. So those are what you would call the absorption lines, which is characteristic again of the atom or the molecule. Okay, and it doesn't absorb everything. So it will preferentially absorb some wavelengths over others. All right. So, and like I said, each atom or molecule has a unique spectrum. So this is the absorption spectrum down here for hydrogen. Okay. And this is the absorption spectrum for sodium. So if you go back to that website, you can see the absorption spectrum. Okay. So instead, you get a continuous band of colors, but in between those colors, you see very dark lines, where those are wavelengths that have been absorbed by the atoms in the sample that you pass the light through. Okay. So hydrogen, that's the absorption spectrum for hydrogen. Again, that 656 nanometer line is there. Okay? It's pretty much just the opposite. The emission spectrum depends on how much energy you're providing the atoms to produce the light to begin with. Okay? So how do you explain spectral lines? You explain spectral lines. This explanation was provided by Niels Bohr, a Danish physicist. So he explained spectral lines as follows. He says, energy of the atoms and molecules is quantized. And what do we mean by quantized? They cannot just have any amount of energy. There's a restriction in the amount of energy, right? Now, if an atom or molecule absorbs light, okay, one requirement is that the photon energy, the energy of the photon of light, must correspond to a difference between allowed levels. In other words, let's say let's say I have an atom with this much energy, E2 right here. In order for the atom to gain energy, the next higher energy, let's say allowed, is E3. Okay. In order for it to go from E2 to E3, the light that must come in, the photon energy, must be equal to E3 minus E2. Okay. If that energy doesn't correspond to E3 minus, let's say it only gives you this much, then it's not going to be absorbed. Okay. In other words, atoms and molecules, you can think of them as being picky. Either give me exactly what I want, or I'm not taking it at all. Okay? So it has to correspond to an allowed energy difference, the difference between allowed energy levels of the atom or molecule. So H nu, the energy of the photon, must equal to delta E. So this equation right here, this is known as the Bohr frequency condition. Okay, now if an atom were to generate light, or a molecule were to emit light, again, the same thing. Let's say it went from E3 to E2, okay? then the light that it produces, the photon energy, the photon that's released when it drops from E3 to E2 must correspond to the difference between E3 and E2. Okay? So if it loses an energy equal to E3 minus E2, then that would correspond to the photon energy. Okay? So that means it's like saying if my bank balance drops from $250 to $100, that means $50 must have left. And so that has to be carried away by the photon. Okay? Now, light that's emitted by photon, like I said, must be equal to the difference between allowed energy levels. Light that's absorbed must correspond to the difference between allowed energy levels. Now, since not every energy level is allowed, you don't expect to see every kind of photon. You don't expect to see every possible wavelength. So you just see those characteristic spectral lines that depends on what the atom or the molecule is. Okay? Because of quantization and because the allowed levels are different for different atoms and different molecules, they all get different spectra. But because of quantization, you cannot just get any color of light from a particular atom or molecule. It's only certain colors that an atom produces, okay, or a molecule. Now, how do you explain a continuous spectrum then? When atoms are more closely spaced together, you could get overlapping spectral lines. So if you have a lot of these spectral lines and they're very close together, you might perceive them as just one band of colors. So if you have very closely spaced allowed energy levels, that tends to happen when the atoms are very close together. So you tend to get spectral lines more when you are dealing with low pressure gas samples. Okay, when you're dealing with solids and liquids, you tend to get bands. And furthermore, if these photons get bounced around so much before they're able to leave and hit your detector, then as they bounce around these different atoms, their wavelength changes. Remember, photons, okay? The wavelength of the photon is related to its momentum, right? So h over p, lambda is h over p. Okay, so if they bounce around, the momentum could change. So there would be shifts in the wavelength as well. Okay, so anyway, if they get bounced around so much, like in a black body, okay, then what you see, the emission spectrum you see would just be continuous. You see all sorts of different photons, different frequencies. All right. So here's an illustration from your textbook about very closely spaced spectral lines ending up forming a band. So this might be what you would see for a molecule of SO2, the absorption spectrum. But if you look at these in high resolution, okay, so this is this thing right here. Okay, and that's a close-up view. If you look at it, you see at very high resolution, you can see there are actually overlapping lines that make up this band. Okay, so molecules tend to have broad bands because of overlapping of very closely spaced lines. Okay, so this is intensity versus wavelength. Okay. Now, modern quantum mechanics tells us that transitions between allowed to, and we'll talk about this later this semester, transitions between two allowed energy levels may or may not be allowed. So it's not enough that those two energy levels are allowed. So let's say 1 electron volt level and the 2 electron volt level is, let's say it's those are the allowed. Let's just say those are two of the allowed levels. It doesn't mean that if I were to give you 1 electron volt of photon, it will be accepted. You might say it could be accepted because 1 plus 1 will take it to 2, right? So that's allowed as far as the Bohr frequency condition is concerned. But there may be other reasons why that may not be allowed. So we're going to talk about that later in the semester. Those are called selection rules. Okay? So let's look at this example that I have here. Let's say the allowed levels of a particle are A. So let's make up a scale, an energy scale here. Let's say it's A. And then the next allowed level is 4A. So A, 2A, 3A, 4A. So this is 0. And then the next allowed level is 9A. So what would that be? 5, 6, 7, 8, 9A. And then the next allowed level is 16A. 10, 11, 12, 13, 14, 15, 16. Okay? So the next allowed level is 16A. Let's say you have a particle that has an energy of 9A. Right? So let's say the energy of your particle is 9A. Then, what are the allowed energies of the photon that this particle can emit? It can go to 4A. So what would be the energy of the photon that it produces? 5A. So your h nu is going to be equal to 5A. What if it were to lose energy so that it ends up being at the lowest possible energy level? What would be the energy of the photon it produces here? Would be 8A. So 5A or 8A would be the only possible photons it can generate, either 5A or 8A. Okay? Yes.
It can go up.
It can go up.
Like 16. Like
yeah. So if some photon comes in, and it can take it to 16. So what would have to be the energy of the photon that comes in if it wants to go from if you want it to go from 9A to 16A? 7A. So if a photon with energy 7A comes in, it will take it to 6. It could take it to 16, provided the selection rules allow it. Okay. What if a photon comes in with energy of 5A? It would only take it to 13A, right? 14A. 9 plus 5 is 14, so this is not allowed. You know for sure it's not allowed. Now, 7A is allowed by the Bohr frequency condition. May be allowed, but you have to know for sure you have to look at the selection rules. Okay? So, here's a summary. Cannot emit anything other than 5A or 8A in this particular example. It may or may not be able to emit energy of 5A or 8A. Okay. This could happen again, like I said, provided the selection rules allow it. All right. So it has to be allowed, but 5A and 8A are allowed by the Bohr frequency condition. Okay. So here's a question. An atom loses 2.5 electron volts of energy as it emits a photon of light. What's the energy of the photon emitted? You should take 2 seconds to answer. Two 2.5 electron volts. If it produces 2.5 electron volts, if it loses 2.5 electron volts, so it loses 2.5 electron volts, that 2.5 electron volts is carried by the photon, right? That's the wavelength of the light that's emitted. How do you calculate lambda? Okay, energy of the photon is hc over lambda. So how do I solve for lambda? hc over E, photon, right? So what's h? 6.626 times 10 to the negative 34 joules second. C is 2.998 times 10 to the 8th meters per second. What's the energy? Yes, 2.50. Electron volt is, I can just substitute here. An electron volt is 1.602 times 10 to the negative 19 joules. Quick conversion right there. Because when you say 2.5 electron volts, that's the same thing as 2.5 times electron volts. All right, so joule cancels out, seconds cancel out. This will give you your answer in meters. What's the answer? 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8th divided by 2.5 divided by 1.602 times 10 to the negative 19. Oops. Negative. 19 negative equals 4.96 times 10 to the negative 7 meters. So what would that be in nanometers? 496 nanometers. What color of light would that be? 500 or not? Huh? Yeah, what color? Visible, yes, but what color? Green. Green. 500 is green. Okay. So you have a spectral line in the absorption spectrum of a molecule occurs at 500 nanometers. What's the energy gap between the two allowed energy levels? Let's make that homework. Turn in next time. Okay. And then this one, what's the answer to this one? This is an easy one. Three lowest allowed levels are 0.5, 1.5, and 2.5. So 0.5. So that's 1. 1.5 is allowed. And 2.5 is allowed. The three lowest levels allowed. Let's say you have a particle with an energy of 0.5 electron volts right here. It will not absorb a photon with energy of what? 0.5 plus 0.5 will only take it to 1, so it will not absorb A. Okay? Will it absorb 1 electron volt? It may absorb 1 electron volt. Depends on what the selection rule is. Will it absorb 2 electron volts? It might. It may absorb 2 electron volts. Okay? It's not guaranteed because we don't know what the selection rules are.
Are we going to learn the selection rules?
Yes, later this semester we'll learn the selection rules.
Not before this first exam.
Then at this point all you can say is may or might. But it's not forbidden, say, by the Bohr frequency condition. It could be forbidden by the selection rule, but not by the Bohr frequency condition. You know for sure it's not going to absorb 0.5 electron volts, right? But you don't know for sure whether 1 or 2 electron volts would be this one right here, A, 4A, 9A, 16A. Those are the lowest allowed energy levels. What would be, let's make that another part of your homework. The homework, question number 2 for your homework. And this one you should be able to do this on your own too. Your allowed energy levels for the hydrogen atom is given by this formula. So what's the lowest energy? For n equals 1, negative 13.6 over 1 squared, so negative 13.6 electron volts. That's the lowest energy. What's the second lowest energy? n equals 2, so negative 13.6 electron volts over 2 squared. What would that be? Negative 13.6 over 4, right? So if this is negative 13.6 right here, this is E1, where's E2? Let's put 0 over here. It's a quarter of the way between 0 and E1, right? So it's E2 right here. Where's E3? Quarter of the way, 1/9 of the way, right? So E3 would be negative 13.6 over 3 squared. So that's 1/9. So this is 1/8, so 1/9 somewhere here. So E3 is over here. Okay. So let's say you have a hydrogen atom that has an energy equal to E1, which is negative 13.6 electron volts. Which of these photon energies cannot be absorbed, okay, by the hydrogen atom? Can it absorb 5.1? 12.1 or 13.2? Which of these cannot be absorbed? You have to figure out what E2 and E3 are. So if you have 5.1, what would it be? Looks like I just gave you the answer. 13.6 plus 5.1, what would it take it to? 13.6 plus 5.1, negative 13.6, right? Okay. 13.6 negative plus 5.1. We will take it to negative 8.5. Where is negative 8.5? Somewhere over here. So that would not be allowed. So 5.1 cannot be absorbed. You know for a fact right away based on the Bohr frequency condition. Okay, 12.1 and 3.2 must take it to where? You can figure that out. It's probably going to take it to E2 or E3. If there's only one correct answer here, then the other two must take it to some allowed level. Okay, whether that level is actually whether it's going to be actually allowed again depends on the selection. And it turns out it is. That red light that you see, this is actually going to happen in the ultraviolet range, okay? That's if you remember your orbitals from freshman chemistry, that's going to take it from the 1s to a 2p orbital, okay? And that red light that you saw in the spectrum of hydrogen, that's called the that's the first in what you call that series of lines you see in the visible spectrum. That's called the Balmer series. That actually goes from the third level to the second level. First one, the red line. Okay, and these are again resources for you to look at for more on this. Okay.